You ever look at something massive, like a skyscraper or a huge bridge, and just wonder, how do they know it's not going to fall down? How do they handle all that weight, the wind, everything? Well, they're not calculating every single ounce of force one by one. Nope, they have a secret, a way to simplify all that complexity down to one single critical point. So let's pull back the curtain and find out what that secret is.
Okay, so it all starts with the real-world problem. In engineering, forces are almost never nice and simple. They're spread out. Think about the weight of snow piling up on a roof, or the constant push of wind against a giant billboard. We call these distributed loads, and they're the bread and butter of structural design. And that brings us to the million-dollar question. To do any useful math with these messy, spread-out forces, you absolutely have to simplify them. You need to find one single spot where you can pretend the entire force is concentrated. Finding this one magic point is the key that unlocks all the other calculations that keep our buildings and bridges standing. But where is it? The big idea here is what we call an equivalent force. We're not just picking a random point. The goal is to find a single force that has the exact same effect on the object. The same push, the same tendency to make it want to twist, everything. We're basically trading in that complex, messy reality of the distributed load for clean, simple point force that we can actually work with.
And there it is. The secret's out. The magic spot isn't random at all. It's incredibly precise. That equivalent force has to act through a very specific geometric location called the centroid. You can think of it as the dead center, the perfect balance point of the load's shape. Find the centroid, and you've found the key to the entire puzzle.
So, if the centroid is the answer, how in the world do we find it? Especially for really weird, complicated shapes. Well, engineers use this brilliant and honestly kind of elegant strategy. It's all about making hard problems easy. You just divide and conquer. First, let's just get this straight. The centroid is the pure geometric center of any shape. That's it. If you cut that shape out of a piece of cardboard, the centroid is the one point where you could balance it perfectly on the tip of your finger. It's the literal balance point. Now, if that object is made of the same stuff all the way through, the centroid is also its center of mass, which is the term you'd use if you're talking about its weight.
And this right here shows you the divide and conquer idea perfectly. Instead of trying to do some insane math to find the balance point of that whole awkward shape on the left, we do something much smarter. We break it down into simple, familiar pieces that we already understand, like the rectangles and triangles you see on the right. We already know where the balance points of those little guys are.
Okay, so let's check out the tools we need to actually do this. Once we've chopped our complex shape into simple bits, we just need two things: a cheat sheet that tells us the answers for the simple shapes and a recipe to combine them all together. This table? This is an engineer's best friend. This is our cheat sheet. For all these common shapes, someone has already done the hard work and figured out the formulas for their area and the coordinates of their individual centroids. Those coordinates, what we call x bar and y bar, are just the x and y locations of each simple shape's own little balance point. We don't have to reinvent the wheel. We just use these as our building blocks.
And here's our recipe. Now don't let the symbols freak you out. All this formula is a weighted average. Seriously, to find the overall x-coordinate of the big shape centroid, you take the x-coordinate of each little piece, multiply it by that piece's area, and then add them all up. That's what that big sigma symbol means. Just sum it all up. Then you just divide by the total area of the whole thing. Same exact thing for the y-coordinate. It just means that bigger shapes get a bigger vote on where the final balance point is, which, makes perfect sense.
All right, enough theory. The best way to really get a feel for this is to actually see it in action. So let's take a shape and find its balance point step by step.
So here's our challenge. We need to find the exact x and y coordinates for the centroid of this shape. And just looking at it, it's definitely not a simple rectangle or circle, so we can't just look it up on our cheat sheet. We're going to have to use our toolkit. Step 1, divide and conquer. You can see it pretty clearly, right? This shape is just made of two pieces we know, a right-angled triangle on the bottom and a semicircle sitting right on top. We'll call them Area 1 and Area 2. And just like that, we have a much more manageable problem. Now, to stay organized, we build a table. For each shape, we calculate its area. Then, using our cheat sheet, we find the coordinates of its own little centroid. For the triangle, its x-bar is just 2/3 of the way over. For the semicircle, we use its formula. But, and this is important, for its y position, we also have to add the height of the triangle it's sitting on to get its true position from the bottom. Then, we just multiply the columns to get what we call the moments.
A times X bar and A times Y bar. Finally, we add up the columns we need for our recipe, and now we just apply our recipe. To get the final X coordinate, we take the total of that A times X bar column, the 96.42, and we divide it by the total area, 41.14. And there it is, our X coordinate, 2.34 meters.
We do the exact same thing for the Y coordinate. We take the sum of the A times Y bar column, that 307.218, divided by the same total area, and we get 7.47 meters. And that's it. We found it. The single balance point for that entire complex shape is at coordinate 2.34, 7.47.
So we found the coordinates. That's great, but so what? Why did we just do all that? Well, let's connect it all the way back to where we started, to real-world engineering.
Finding the centroid is, well, it's everything. It lets an engineer take a messy, spread-out load, like the entire weight of a building, and replace it with one single point force. And once they have that, they can easily figure out how strong the foundations need to be. It's why a crane can lift a heavy, awkward steel beam without tipping over. The operator knows exactly where that beam's center of mass is. It is absolutely fundamental to designing anything that's stable and safe.
This whole divide and conquer approach is just an incredibly powerful way of thinking. It turns these overwhelming problems into a series of simple, solvable steps. So the next time you see a cargo ship stacked high with containers, or maybe the wing of an airplane, try to see the simple shapes hidden inside the complex one, and ask yourself, where do you think its balance point might be?